So just give me a second. I am sharing my presentation. I hope my screen is visible to you. Can anyone confirm?
Yes, sir, the screen is visible.
Okay, thank you. So, like Mansi has just mentioned, the topic is with respect to deep learning and convolution neural network. But before we begin with deep learning, let's try to understand why this particular topic is a part of workshop, which is mainly based on network science. Right? Okay. So, uh, in the previous sessions, you must have heard about how we can represent any particular domain related ideas in terms of graphs. For example, if we talk about chemistry, then molecules can be represented as graphs on networks. So what is the idea when we try to represent molecules in terms of graphs? Then the atoms will be represented by nodes, and bonds between different atoms will be represented by edges. And along with this, we can also associate features associated with each node. For example, we can talk about atom type, we can talk about bond type, we can talk about charge, and so on. So once, let's say, we have this kind of representation with us, then what can we do with respect to this representation? That is the next question. Okay. So for that particular purpose, we consider this particular term for the very first time, GNN. GNN stands for graph neural networks, right? So let's say we have one objective. Our objective is to find out whether the underlying drug will inhibit certain bacteria or not. So in other words, we are just trying to identify whether this particular molecule structure will fight against some specific type of bacteria or not. So in order to solve this particular problem, we can apply GNN. So we are not going into details as of now. We are just trying to understand what is the we can say applications of graph neural networks in today's world, so that we can motivate and study about it in detail, right? So this is one of the application where after performing this graph neural network on this particular molecules, you will be able to say whether that particular molecule will inhibit a particular certain type of bacteria or not. So this is one application. There are sub applications also. For example, let's say you have derived 100 candidates based on the experimentation which you have just done. So now what you can do, you can recommend this 100 candidates to chemists for further processing, and then they can identify whether a particular candidate is antibiotic or not, right? So this is one of the most popularized success story of graph neural network, where a new drug named helicin was found, and which is antibiotic. And then there are other success stories also which are published in BBC or Financial Times and so on. So whenever you hear that using AI, scientists found some new antibiotic drug, at that time the on in the background GNNs are responsible for them, right? So this is in drug discovery, we can say this particular domain is very much helpful. Apart from this, we can also consider, let's say, if we consider Indian people who are above age 70, then roughly 70 to 80% people who are above age 70 will are taking at least 3 drugs in a day, right? So now, if you are combining different drugs together, let's say they are taking drug 1, drug 2, and drug 3, and in Indian markets, in the Indian market, Indian drug market, let's say you are having 1,500 different drugs corresponding to diseases which are popular for this particular age range. So if you actually want to identify which kind of side effects will be generated if this if 3 drugs out of this 1500 number of drugs will occur, then you need to actually demonstrate this many different scenarios, right? 1500 choose 3. So this is a very large number, and it's not practically possible to consider all different combinations and do experimentation on real human beings. So at that time, we can apply GNNs, and GNNs provide us fantastic results for this kind of identification of drug side effects also, right? So this is with respect to drug industry, we are getting very good results, right? When practically people are using it, right, in today's world. The second motivation is you can all of us know about Google Maps, right? So basically, again, we can consider them as graphs. So what is the idea here? Whenever you consider intersections of different roads, then those intersections will be represented by nodes, and edges between different intersections are nothing but roads, right? So that is the idea of representation. And along with this, you can have different parameters also. For example, what is the length of the road? What is the current average speed of vehicles on that particular road on a particular given timeline? And as well as you can also consider some historical speeds and so on. So by considering this representation and applying concepts of graph neural networks, actually this improvement is done on Google Maps. And what is the improvement? Improvement is on estimate of time of arrival quantity. So let's say you are traveling to a particular city, let's say Delhi, and currently your Google Maps is telling you that the time required to reach to your destination is, let's say, 2.5 hours. So how much accurate this particular information is? So in order to improve its accuracy, this again GNNs are used, and you can see the results. Now the improvements are very high, right? For certain cities, the improvement is above 51%. So now that means this whatever this accuracy of Google Maps are improved significantly in terms of estimated time of arrival with the help of graph neural networks. Okay, so this is one way of looking at it, that we have just considered two different but important domains where graph neural networks are useful. But apart from that, if we talk in terms of research, or if we talk in terms of academics, then we are interested in publishing papers also. So if you consider top 50 keywords or of ICLR 2021 conference, then you can see that graph neural network is at third position, right? So that means many people are writing down papers on this particular domain. And apart from this, you can also see the keyword usage. So you can see that the usage of this particular keyword is increasing drastically, right? So we can say that GNNs are currently experiencing their ImageNet moment, right? So that means a lot of people are working on this particular domain. So now this is all about graph neural networks. It's fine. It seems very interesting and exciting, and we can do a lot of research in this domain. It seems very promising, right? But the question is how to start with it. So in order to do so, basically, before we talk about graph neural networks, so the very first topic which we are going to consider uh, is nothing but graph convolution neural networks. So before we talk about this graph convolution neural networks, we must understand about convolution neural network. And before we understand about convolution neural network, we must know about basics of deep learning, right? And all these things are, if you talk about implementation, then whatever terminologies which I am going to discuss today, all are equally applicable for GNNs also, right? So that means if we talk about, so let me just throw some keywords to you. For example, if I talk about dropout, then the concept of dropout is present in deep learning as well as in CNN and as well as in graph neural networks also, right? If I talk about epoch, then epoch is present in deep learning as well as a convolution neural network as well as GNNs, right? So that means the terminologies which I am going to explain today are all are applicable for implementations of GNNs also. So therefore, this is a very much important talk, because if we skip this, then we won't be able to understand the workings of GNNs. And also, with respect to my talk, I want to highlight that I will mainly focus on concepts, terminology, as well as on terminologies. I won't give you too much math, right? We will just mainly discuss about ideas related to this fields, right? And why we are doing so? Because if we just compare, let's say our normal domain. Let's say if I tell you to sort n numbers, right? If I tell you to sort n numbers, then what you will do? You will just write down one algorithm and then you will implement it, and I will get a specific answer with 100% accuracy. So that means if 100 numbers are given, then you will come up with an algorithm which will definitely sort this, either sort this 100 numbers, or there will be some bug which you will be able to eventually recognize and eliminate, right? So that is the idea of simple algorithm, where you give specific input and you will definitely get a certain output, and you can also give rigorous mathematical proof why your proposed solution will work. Whereas deep learning is completely opposite. For a given task, if let's say your task is to given set of images are given to you, right, and your task is to identify whether a particular image is of cat or dog, right, something like this, and then you are saying that your accuracy is 97%, which is better than the existing models to solve the same problem. Then no one will ask you for the rigorous mathematical proof why your proposed solution is giving better results as compared to existing models. Certainly, if you are publishing at a very good place, then they will ask for intuition as well as some kind of mathematical reasoning for this particular result. But certainly, there won't be any rigorous mathematical proof for your findings. So that is, in some sense, advantage in working in this particular domain, because most of the work will be done by free open source libraries. All you are supposed to do is you are supposed to know about different hyperparameters and experiment, right? If you know about different hyper, so what do you mean by hyperparameter? So hyperparameter means parameters whose value can be fixed by the programmers. So values which we are going to set, they are called hyperparameters. So only thing which you need to understand regarding this particular domain is what is the importance of different hyperparameters and how to experiment with them so that we can improve. So that is that. Okay. So now I guess we can start with the formal talk on deep learning. So this is the structurally, if we try to represent, then we can say artificial intelligence is one of the way of doing science, and machine learning is again one of the way in which we do artificial intelligence, and deep learning is nothing but it's a subset of machine learning, which is nothing but class of algorithms which is structured way of doing machine learning, right? So if we go top down, then in science basically we talk about different phenomena. The phenomena can be natural or it can be man-made. In artificial intelligence we mainly talk about intelligence. So what do you mean by intelligence? Intelligence means the abilities. We talk about different abilities, for example, ability to reason, ability to learn, ability to plan, and the most important one is ability to solve problems. So all these are nothing but they are forms of intelligence, we can say. I give you one statement. From that particular statement, if you infer something, then it's nothing but ability to reason. If you are learning this particular new domain, then it's nothing but you are able to understand about it, and you are getting to know about different concepts, and you are learning it. So that is nothing but ability to learn. There is ability of plan also, based on the knowledge of your task, how you are going to plan so that you can solve the underlying problem, right? So like that. And when we talk about machine learning, then okay, so now again, every time a machine tries to do something, and if it success, then what we do, we set the bar, we change our target. We say that now this is not intelligence. Now my intelligence is somewhere here. So what we are doing is every time we are changing the in some sense level of intelligence also, right? And we are expecting more and more from a machine in some sense. And in machine learning, we try to encode intelligence in man-made devices like computers, right? And our main focus is on deep learning, which is, like I mentioned earlier, it's nothing but it's a subset of machine learning class of algorithms which we are going to talk about today. So why do we need to study deep learning? So what are the applications which are specific to deep learning? So let me consider this simple program, simple application where what we are doing, the task is to sort, let's say, 1,000 postcards, right? And on the postcards, this pin code is written, and the pin code is not written like this digitally, but it's handwritten. So basically, what you need to do, you need to identify each digit, right? And then you need to sort this 1,000 postcards. So now this task is very much difficult for even humans, because now someone can write 9 like this, some other person may write 9 like this, right? Some person may be left-handed, some person may be right-handed. It may be possible that someone writes one in the middle of this particular box, whereas someone else writes one at the very left side of this particular box, and so on, right? So this seems very tedious and time-consuming task, but it turns out that deep learning applications are application of deep learning can solve this particular problem very efficiently, right? Efficiently in terms of time as well as accuracy, right? So with very high accuracy, the deep learning solution will solve this particular problem. Similar kind of problem when we try to decrypt checks, right? So let's say this amount is written in dollars here, and the same amount is also written in terms of words also, right? And now you want to match whether these two are same or not, right? So again, deep learning will help us to do so. The most popular applications, I guess all of us know about it, that whenever you want to recognize any image at that time, you can apply deep learning, right? So not just simple images. Even if you change the location of the image, right? So let's say the image is, instead of center aligned, it's left aligned. Or maybe the same person is there, but due to lockdown, he has grown facial hairs and so on. But still, the deep learning system will able to recognize that particular person, and that too with high accuracy. There are some other applications also. For example, let's say this kind of data is available for some experimentation related to physics, and you are interested in finding out this specific pattern, whether it is present in this data or not. So again, if we do it manually, then it's very much difficult, but deep learning does this very nicely. And other applications are related to text to voice translation and so on. And you can also estimate population using deep learning, right? Again, you can eliminate noise from your pictures, right? Like this. So if this is my input, then deep learning will give me this one as my output, right? One more application, again, there is some noise here. The image is not properly visible in this particular region. Then what the system will do? It will check its database. Let's say this is the reference image which will be identified by the system automatically, that this is the nearest image for this particular input, and it will automatically correct it like this. Okay, so now before we go further, let's talk about two important keywords. First one is unsupervised learning, and the second one is supervised learning. So whenever we talk about this particular substring, supervised. So supervised means labeled. So labeled are nothing but they are for representations, values which are given by experts, right? So for example, if I have one image of handwritten one like this, and expert will assign its corresponding value to it, which is nothing but 1. So this is nothing but my label. So whenever we talk about supervised learning, at that time we have objects, and along with objects we have its value, which is represented in terms of labels, and its value is correct value. So that we need to remember that whenever we talk about supervised learning, whichever labels are assigned, those labels are actually correct values. Right? There is no ambiguity or incorrectness in these labels. So now we are talking about unsupervised learning. Unsupervised learning means we have set of objects, but there is no underlying labels for them. And you give this to a deep learning system, then so let's say this you are you try to identify uh, some ancient icons, Asian symbols, and you found these symbols which are a part of one bowl, let's say, and now you want to identify what is the relevance of each symbol with respect to other symbols. Then the deep learning will system will give you this as output, and now you will be able to get some ideas that this is your one class where this kind of symbols are used, this is your second class where this kind of symbols are used, this is your third class, this is your fourth class, and this is your fifth class. So in some sense your deep learning system has given you clustering on this data, right? And now based on, let's say, some parameters like weights as well as height, these are different data points, and then you can classify them. You can again make clusters like this. If you draw this straight line red, and then whichever points come above this particular straight line, we will say that they are object type 1 and these are object type 2, like this. And you can also have this kind of curve where you try to fit as many data points as you can, so that you can again classify. Right? Classify means you want to give labels based on the features of data items. So based on the features, we have represented them here graphically, and now with the use of curve we are trying to classify them, right? So the points which come above this curve belong to class 1, and let's say point which comes below this particular curve will fall in category 2, like that. So based on length and weight you can do this kind of classification. So let's say the red circles are corresponding to, let's say, bananas, and this blue squares are corresponding to, let's say, grapes, right? And then we are trying to classify them. So situations may arise like this. For example, for this kind of distribution, which curve is better? For example, we want to classify again these two objects. So where should we put our curve so that we can say that our classification is correct? So again, it's a policy decision. For example, which item is important for me? If these circles are important to me, then I will try to cover all the circles like this, and they are correctly classified here. And if squares are important for me, then I will select this kind of curve where you can see all the squares are classified correctly, but there are some circles which are misclassified. So again, it depends upon your application. Now, mainly we are going to focus on supervised learning because it's very easy to verify whether our output is correct or not if we do experimentations with respect to supervised learning, because now, as you can see, each data item along with each data item there is one label associated with it, and this label is unique, right? Okay, so now before we go further, let me do one simple experimentation. So now what I'm going to do, based on the people who are attending this talk, I'm going to write name of few. So the first name is Aarti. The second name is Ashish. Then Divya. Then Girish. Then Kalpana. And then Minakshi. Then Rekha. And finally, Dr. Muskan. Now we'll do one simple exercise. So what is the question here? The question is, one image is given to you, and let's assume we haven't seen this particular animal in our life. We are seeing this particular animal for the very first time, and the question is this particular animal is koala animal? That is the question. Okay. And in order to answer this particular question, you have made this team. So what is the idea of this team? They are going to do a teamwork in order to answer this particular question. So now the focus of Alti will be on eyes of this particular animal, right? So the task of Alti is to focus on eyes and tell Minakshi, report to Minakshi whether this particular eyes belong to koala animal or not. Similarly, Ashish will focus only on nose of this particular animal and then report to Minakshi. Similarly, Divya will focus on ears and Girish again report to Minakshi, and Girish will focus on legs and Kalpana will focus on tail, and Girish and Kalpana will report to Rekha, right? And Minakshi and Rekha. So what is the task of Minakshi now? The task of Minakshi is to give result regarding whether the face of this particular koala animal is present in the image or not, right? So this task will be performed by Minakshi and she will report to Dr. Muskan. And the task of Rekha is to say whether, because she is getting knowledge of legs and tail, so she will give decision regarding remaining body of this particular animal, whether this particular body belongs to koala animal or not. So that information will be given to Dr. Muskan by Rekha, right? And what is the task of Dr. Muskan? She will, based on this face and body, finally she will answer this particular question, whether this particular image is of koala or not, right? So this is the idea, right? So finally, Dr. Muskan will compute some number, and based on that particular number, she will give final answer whether this particular animal is koala or not, right? So now let's start this process. So since Alti is not sure whether this eyes belong to koala or not, so she will give. She is taking some inputs. That is for sure. All of this are getting input from this image, right? That is for sure, because then only they can answer, right? So they are taking this inputs, and Alti will multiply some number with this particular inputs so that she can give her prediction to Minakshi. So let's say Alti is circulating number 1 by 2. So that means in some sense, she is saying 50-50. There are 50% chances are there that this particular eyes belong to koala animal. Ashish is seeing this kind of nose for the very first time. So he's guessing that this particular animal, this nose doesn't belong to koala. So he will transfer 0 to Minakshi. And Divya, again, she is transferring, she is not sure, so she is transferring 1 by 2 to Minakshi. Again, there is no tail visible in this particular picture. So Kalpana is transferring 0 here because she can't see tail, so she is not sure. And Girish, he's able to see legs, but he is not sure whether they are corresponding to koala or not. So he is transferring 1 by 2 to Rekha. Now, this is done with respect to this 5 members. Now, what Minakshi will do? She need to somehow say whether this face belongs to koala or not. So what she will do? She will give some importance to eyes, some importance to nose, and some importance to ears. right? And then depending upon these three values, she will give some result. So how she will do it initially? So initially she is going to give same importance to all the three features. So 1 by 3 into eyes, let's say, plus 1 by 3 into nose, plus 1 by 3 into ears. So this is her initial equation of giving decision to Dr. Muskan. So let's substitute values. So these are nothing but importance or weights given by Meenakshi. So she is giving equal importance to eyes, nose, and ears initially. So now what will happen? We'll get one new number, 1 by 3 into 1 by 2, plus this will become 0, plus 1 by 3 into 1 by 2. Right? So basically this is 1 by 6 plus 1 by 6, which is nothing but 2 by 6, which is nothing but 1 by 3. So this result will go to Dr. Muskan. Similarly, Rekha will do the similar computation. So initially she is giving same importance to legs as well as tail. So she will say 1 by 2 into legs plus 1 by 2 into tail. And with respect to this, the score is 1 by 2. So the first entry is 1 by 4. The second entry is 0. So she will transfer this 1 by 4 to Dr. Muskan. So now again, Dr. Muskan will initially give same importance to face as well as same importance to body. So she will calculate this new score, which is nothing but 1 by 2 into 1 by 3 plus 1 by 2 into 1 by 4. So if we simplify this, then finally we will get 7 upon 24. And since this number is less than 0.5, she will tell me that this image is not of koala animal. Now she will just tell me this result, and I will tell her, no, you are wrong. This is actually an image of koala animal. So now what she needs to do now? She will come back and first she will contact with Meenakshi and Rekha. She will tell them that in future, if you see this kind of image, then make sure you give me correct answer. You need to supply me higher weights, not 33% or not 25%. It should be 100% next time. Now Meenakshi will contact to this three now, Alti, Ashish and Divya, and she will tell them next time if you see this kind of eyes or nose or ears, make sure you give me maximum weights, not 0. You should give me 1. Similarly, Rekha will contact to Girish as well as Kalpana and tell next time if you see this kind of scenario of legs as well as tail, then make sure that you give me the correct weights, not 1 by 2 and 0. Right? So now we will repeat this process, let's say 10,000 times. And let's assume this individual people don't have memory. They are focusing only on this tiny little attributes. Aarti will only focus on eyes, Ashish will focus on nose, Divya will focus on ears, and so on. After 10,000 iterations, so every time what will happen? A new image like this will be given to you, and your team will perform some computation and then give me the answer. Dr. Muskan will give me the answer, and I will tell her whether her answer is correct or wrong. So over the period of time, what will happen? After 10,000 iterations, this individual members will become expert now. In one shot, they will be able to give correct answer with high accuracy now, because they are familiar that this eyes are of this particular koala animal, this nose is of koala animal, and so on. And accordingly, they will. The most important thing with respect to this exercise is, if you notice, then over the period of time, this weights will also change. Over the period of time, Meenakshi will realize that as compared to other features, nose is very much prominent in this particular koala animal. So what she will do? She will give higher importance to nose now. So her equation is not no longer 1 by 3, 1 by 3, 1 by 3 now. Her weights are not 1 by 3, 1 by 3, 1 by 3 now. She will give more importance. Let's say 1 by 2 importance is to nose now. And remaining 25% importance to eyes. And remaining 25% importance to ears now. So this modification will be done by Meenakshi over the period of time after this 10,000 iterations. Similarly, Rekha will understand the importance of legs is more, because in some images even tails are not that much visible also. So what she will do, she will give 3 by 4, let's say 75% importance to uh, legs and 1 by 4 importance to tail, right? And now this team will work very nicely, and they are going to predict whether the given image is of koala or not. What I have just explained you, artificial neural network. Each one of this member is nothing but they are neurons, and they are interacting like this. Okay. So now we are anyway going to see this particular concept formally, but this is the idea of neural network. So first, you will get training. Training means you are going to you can reuse these images as many times as you want. These are your training images, and finally on 100 images you are going to give test. So test images you can't use multiple times. You are supposed to give test exactly once, because otherwise if you see the images which are present in test earlier, then it's a case of cheating, which is not allowed, right? So test data will be visible exactly once, and you can reuse this training data as many times as you want. And each iteration, what you are doing, you are finding out whether your prediction is correct or not. If it is correct, then it's fine. If it is not, then you are finding out what is the error, and that information is propagated backwards, which is called back propagation. We are going to formally learn about all this, but this is the idea. So now, if this is the case, then one can ask how this concept of deep learning is different from distributed learning. Because ultimately what you are doing, you have divided this big task into this subtask, and this subtask can work parallelly also. For example, Aarti can focus only on eyes, and at the same time Ashish can focus on nose, and so on. So here there is a major difference which I would like to highlight. So in the case of distributed computing, we are supposed to tell which features are important, and uh, what should be the focus of each machine. Whereas in the case of deep learning, the features will be identified automatically by the system. So we are not supposed to tell what is the task of this particular neuron. It will automatically identify what is supposed to be done. Right? So we'll see how, but this is the difference which I wanted to highlight. Okay, fine. So let's continue. So like I mentioned, so available data, so generally what we will do, roughly 70 to 80% data we will use for training, and we will learn, and the remaining data we are going to use exactly once. And here what we are, since the data is labeled, right? Since this is supervised learning, we already know its correct answers. It's like you are the answers key is already ready with you. Now you can compare your prediction results with the correct results, and then you can give the final accuracy, right? So accuracy on test data matters. For example, on training your accuracy is around 85%, but this doesn't make much sense because this training you can reuse again and again, whereas for testing data you are going to use them exactly once. So, and this is unknown to the system, so whatever you perform in test, that matters. So if your accuracy is around 85% in with respect to training, then generally you will get accuracy of around 80% or 80 to 82% in testing. Generally this is less, testing accuracy will be generally less than the training accuracy. Okay? So now we are ready to talk about MNIST dataset. So we can say it's nothing but hello world of machine learning. So what is the idea of this dataset? So again, it's a collection of 70,000 images, and each image is of size 28 cross 28, right? So you will get this particular number. 784 pixels are present in each image, and it's a grayscale image. So that means either pixel is white or pixel is black. And again, this image set contains handwritten images, and each image is placed at the center of your image. Each digit is placed on the center of the image. So this 0 is in the center, like that, right? And again, different writers have written this numbers, so you can see that a lot of variation is there. For example, you can see variations in writing 9, right? Some are left-handed, some are right-handed, and so on, right? Some are using thick ballpoint, some are using thin, some are using some different kind of pen, and so on. Okay. So what happens if we don't use concept of deep learning? In that particular case, what will happen? You will basically your results will delay upon this kind of rules. You will identify whether horizontal line is present or not, whether this diagonal line is present or not, and whether they are meeting or not. And again, if some people can add this second horizontal line also. So you will write down this kind of rules, and then you try to answer the question whether the particular digit is of 7 or not. So this kind of thing is called expert system, where, or it's called rule based system, where you just write down rules corresponding to a particular task. But this won't work in real life. For example, it's the same kind of thing I'm proposing for, let's say, air traffic control. Then what will happen if you miss some rule, or let's say if you didn't consider a one particular scenario, then accident may happen, right? So this is the limitation of this expert systems or rule based system, where and again you need to get experts and on that particular domain, then only you will be able to solve the problem. For example, if I give you brain images, right, or x-ray images, then we first need to contact doctors. We can't apply our solution directly without tools, right? So that is the limitation of this expert system, and that's why we are talking about deep learning. So now the next question is why it is called deep learning, right? Why this particular word deep? So the idea is whichever modules which we are going to consider in deep learning, we are going to stack them up like this, one above another, like that. And now we are at top. Let's say you are standing here, and now you are seeing down, and then you will say it's deep learning. This name is just stuck. It may be possible that researchers would consider this particular kind of scenario where modules are stacked left to right. Then maybe they could call it wide learning or something like that. Right? But the name is deep, which we all know. Right? So, for example, let's we don't care about this white box as of now, but what should happen if we pass our MNIST data set to a deep learning system? What should happen? In some sense, we know that total 784 different pixels are there, and if we consider matrix like this 28 cross 28 matrix, then we can't directly pass this particular matrix to our neurons. So therefore, what we are going to do, we are going to first flatten this particular matrix. What is the idea of this particular word, flattening? What we are going to do, we are going to write down, we are going to convert this two-dimensional matrix into one-dimensional matrix. First, we will write down all the entries of first row, then we will write down all the entries of second row, and so on. So we will get 784 different values, and those values will be provided to neurons which are present at the input layer. And now, if we consider about outputs, then we know output can be anything between 0 to 9. So therefore, we want 9 different neurons towards the end also, which will tell us which number. For example, if I give image of 5, then I expect that this particular neuron will fire. So that means its value will be higher as compared to other values, right? So this understanding is required, understanding of input as well as output. So now, can anyone answer me? Let's say I want to design a deep learning system where my task is to just tell whether the underlying animal is koala or not. Then how many neurons are required here? You can speak, or maybe you can type. So here 10 different values are possible, so 10 neurons are there. Now my question is, so instead of koala, let me consider a simple animal. Let's say whether the given image is of cat or not. Then how many neurons are required in the output layer? And options are 0, 1, 2, and 10. You can guess, it's fine. This is very much important because if some task is given to you, then you need to first you should be able to identify how many different outputs are possible, and accordingly you need to fix number of neurons at your output layer. So here I know 10 different values are possible and I have given 10 neurons. So what if my task is binary? This is kind of binary classification. Either my answer is uh, yes or my answer is no, right? So what do you think, how many neurons are required? Any answers? I hope I am audible. Can anyone confirm?
Yes, sir, you are audible.
Any answers for this particular question?
Two.
Okay, so correct answer is 1, because with one neuron you will be able to say whether that particular image is of cat or not. If this particular neuron fires, that means if that particular neuron has high value, then we can say it's cat. If it is having low value, right? So we'll see how to get those configurations. But using single neuron, you will be say whether that particular image is of cat or not, right? So for binary classification, just one neuron is sufficient. In other cases, it depends upon how many classes you have, right? Okay, fine. So now, and again, you can also have extra neuron, and with two also you can do it. But where there you need to be specific. First neuron will be for cat, and second neuron will be for not cat in that particular case. Okay, fine. So now, what is neuron? Let's understand them formally. So they are extremely complicated if we talk about real life neurons which are present in our brain. So and what they are going to do? They are going to take inputs using this dendrites, and then some biochemical process will happen in the nucleus of your neuron, and then you are getting different kinds of inputs. Currently also you are maybe hearing to this particular talk. At the same time you are also worrying about some other pending tasks, and then you some process will happen here, and depending upon how much importance you are giving, for example you are giving w1 importance to this particular event, and W2 importance to your pending task, and so on. And then you will think about, you will compare different inputs, and you will finalize which one is more important for you. And depending upon that, so you will get some value, some impulses here, and then you will finalize whether you should continue listening to this particular talk or you should leave, something like that. So these actions are dependent upon which kinds of inputs you are getting and how much weightage you are giving to each input, and then you process it, and then if some threshold value is passed, then you do some action, right? So this is kind of we can say deep learning is currently going on in your mind also when we are learning this particular topic in some sense. Okay, so now this neurons are real neurons are extremely complicated, and there is no way we can replicate them in any scale. But still, people are calling it neurons, but the original name was Perceptron. So what is the initial model of Perceptron? So it's very much similar to what we have just seen. So the idea is like this. You are getting some inputs like I mentioned earlier. So this, let's say I'm considering 4 neurons. So they are going to get 4 different inputs. Consider them real numbers also. So this system considers 8 different real numbers. 4 are inputs and other 4s are nothing but how much importance we are going to give to this different inputs. They are nothing but they are called weights. And now what you are going to do, you are going to multiply your input with weights. This input is this much important. So multiply both of them and you will get one number here. Let's say x1. Similarly, here you will multiply input 2 with weight 2. You will get x2, then x3 and x4. Finally, you will add them and here you will put some threshold. If your final answer is greater than 0, then you will do something. Otherwise, you will do something else. It's like that. So it's very much similar to our actual neuron. Now, this notation is very much abused. So instead of, so generally people draw neuron like this. So in this kind of neuron, you can see only inputs are there. Weights are missing. So whenever you see this in your mind, you need to understand that actually this is happening, where weights are represented in edges. So that means inputs, and this is to be understood that whenever you are thinking like this, at that time, you are actually performing this multiplication, right? So this notation is very much abused because weights are the most important thing. You can't change input. Can you change the input image? No. Only thing which you can change is weights. So weights are very much important, and unfortunately, in some of the literature, you will find that weights are not present, right? So in your mind, make sure along with each input, weights are associated, and you are supposed to multiply your input with weights, and then you will be having one threshold function, right? Like this, and then you will do something. And there is one more input you can consider, which is nothing but bias. So you can say by default you are going to give some value to this, let's say z, which is nothing but your bias. For now, we can think like that. Okay. And why I'm saying we can't replicate the real neurons, because we have done this particular task of identification of koala, but actually if as humans we don't require this much effort. All we need to do is we need to just look at one of the image and we can straight away say that whether the next image is of koala or not, right? For we just one look of this image is sufficient to answer any number of questions. But for deep learning system, it requires thousands and in some cases millions of images to answer this kind of question. So therefore, this neuron name is kind of abusive in terms of behavior of actual neurons. Okay, so let's continue. Now, if we consider more than one neurons, then we will get neural network like this. Now, the terminology is very much important. There is a notion of fully connected layer. What is the meaning of this word fully connected layer? Fully connected layer means if I say layer 2 is fully connected, that means each neuron of layer 2 is connected with all the neurons of previous layer, which is nothing but layer 1. So you can see each red neuron is connected with neuron 1, neuron 2 as well as neuron 3. If I want to make layer 3 as fully connected layer, then what I need to do? I need to connect this 4 with this 4 red neurons. Similarly, I need to connect this 5 with this red 5 with this 4 red neurons, and this 6 with this 4 red neurons. Now I can say layer 3 is also fully connected layer. So whenever a layer is fully connected, that means it has all the possible connections with the previous layer. Okay. So again, like I mentioned earlier, why it is called deep learning? Because as you can see, what will happen if you understand, then these layers are put stack wise from bottom in the bottom up manner. So here is your input. right? This is your layer 1, this is your layer 2, this is your layer 3. So now if you are standing here, let's say you are standing here somewhere, then you won't be able to see this layer. So therefore it's called hidden layer, right? So if I give names, then I can say this is your input layer where input will be processed. This is again hidden layer because from above you won't be able to see this, right? And this is your output layer where neurons are there and the output of these neurons are corresponding to actual output of your problem. So you can see this particular representation is not symmetric, it is asymmetric, because you can notice here in output layer there are neurons, whereas in the input layer there are no neurons, there are only inputs, right? So therefore this notation is not symmetric, right? Okay. Now this is the most important thing, activation functions. So like I mentioned, after coming here in neurons, let's say your value of Z is something. So how will you decide whether to take a particular action or not? So at that time, you will check the output with some threshold, and depending upon the value after you get this activation function, you will do something, right? So here also what we are going to do, we are going to use different activation functions, and the most important activation functions are listed on this particular slide. So 90% of times in deep learning system as well as in GNNs, we are going to see about ReLU or sigmoid or 10H, right? So we are going to use these concepts in hands-on also, so therefore they are important, and if you know them properly and if you use them correctly, then you will be able to solve many problems. So let's learn about ReLU activation function. It's called rectified linear unit. So what is the idea of ReLU? Let's say my input is B, then this ReLU function will give me output as maximum of 0 comma b. So that means if my input is negative, let's say my input is -5, then maximum of 0 comma -5 is 0, so my output will be 0. But if my input is 5, then my output will be 5, because maximum of 0 comma 5 is 5. So you can think like this: for positive values it will give me as it is result, for negative values it will give me 0. And it makes sense, because what we are doing here, we are actually trying to classify things, right, with respect to supervised learning. So there is no way we can say that there are minus 25% chances that this particular image is of cat, right? It doesn't make any sense. Minus 25 doesn't make any sense, right? So therefore we said 0% chances that this particular image is of is not cat, right? So therefore it's defined like this ReLU. Okay. Other activation functions are sigmoid and 10H, right? So sigmoid, you can see its shape. It's like S shape, right? So S shape, therefore it's called sigmoid. And another one is 10H, right? And there you can see their ranges, right? So one is going from -1 to 1, and the another one is from 0 to 1. Okay. Now, this is not activation function actually, softmax, but it's very much useful, and we are going to use them many times. Why? Because let's say you are doing classification task, and there are three categories for of possible outputs. There are object class A, object class B, and object class C. And you are saying A score is, let's say, 15, B score is let's say 5, and C score is, let's say, 37. But these things, if I add these three, then I will get 67. This is not probability distribution. They are kind of logarithmic values of likelihoods, something like that, formally. So I'm not going formally right now. My objective is to just explain different concepts which are associated with deep learning. So what we are going to do, basically, we are going to get probability distribution out of this. So how we will get? So basically 15 divided by 15 plus 5 plus 37. If we get this value, then that will be the probability of n. Similarly, 5 upon 15 plus 5 plus 37, if we get this value, then it will be probability of B. And similarly, probability of C will be 37 upon 15 plus 5 plus 37, something like this. So these values will be directly obtained by softmax function. So if we call softmax, then directly we will get probability distribution, so that if we sum these probabilities, then we are going to get one, and it will be very easy to differentiate which particular object class is dominating, right, for a given image, right? We can do that, right, with respect to softmax. Okay. Now, how to learn from mistakes? So, for example, you are doing predictions, and your prediction values are two only. Let's say value 1 and value 2. Let's say P1 is corresponding to, let's say, dog, and P2 is corresponding to, let's say, cat. And you already have labels, but for given image, let's say I supply one image of cat. Let's assume this is cat. I supply one image of cat, and your prediction is saying 70% dog and 30% cat. Let's assume I have used softmax so that I will get this kind of probability distribution. But now the question is how to compare this 70% and 30% with my label. My label is cat only, and cat is just one dimension. How to get vector like this? I have one vector corresponding to my answer of this question, which is nothing but 0.70 and 0.30. Whereas the known value is just single, which is nothing but cat. So that means I need some mechanism which can convert this single value into this matrix of size 2 cross 1, right? So in order to do so, there is one concept which is called one hot encoding, right? So the name seems very fascinating and difficult. It seems very difficult concept, but it's nothing. All you need to do is you need to convert your label into vector. For example, in this particular case, what will happen? If my label is cat, then I will represent it like this. Corresponding to dog, I will put 0. Corresponding to cat, I will put 1. And now I have two vectors. This is my prediction, which is nothing but 0.7, 0.3, and this is my actual answer. Now I can compare this two. I can apply. There are many error formulas. I can consider one particular kind of error, and then I will be able to get the error for this particular prediction, right? So the idea is how to convert this label into this vector. The concept is one hot encoding. So for example, I have written this colors, this 8 different colors which were introduced by the crayon company for the very first time. So what I'm going to do, I'm going to assign different digits to each color, digit 0 to red and digit 7 to black. And let's say my answer for the given image, let's say my answer is black. Then how I'm going to represent it? I will put 0 for all other colors, and I will put 1 corresponding to black. So this is the idea of one hot encoding. Similarly, let's say if my color is green, then I will put 1 at index 3 and all other values will be 0. Right? So the importance is you want to you want to apply error formula, you want to use error formula at that time. There is a mismatch in terms of dimensions. So to solve this, in other words, what we are doing here is if the image is of cat, then we are saying 0% chance it's an image of dog. So we are putting 0 here. You can also think like that, and then you can apply error. So now the next question is, what will happen after you get error? Now some changes are required in weights, because only thing in this particular network which you can change is nothing but weights with respect to neural network, right? Inputs you can't change. What, for example, your input is some real number, let's say 0.3 and 0.2, then you can't change these two numbers, right? How much importance you are going to input which is coming to A, that you can change, right? So this is nothing but weights associated with A, right? And there are two weights. One is corresponding to X and second which is corresponding to Y, right? So WX, WY, this you can change. So let's say what you are doing now, let's say this is your weight X and you are keeping it 3 and you are just checking different possibilities with respect to Y. So you will range y from -3 to minus +3, let's say. You are just seeing what is happening with respect to error. So basically, I will just written integers, but you can actually take real numbers also, because in between there are many possibilities. And then you will increment x. Let's say now instead of 3, I will take 4 value of x, and then again I will repeat the same thing. I will consider different possibilities with respect to weight y. So basically, I will get different points associated with this combinations, right? I have considered 14 different combinations, and corresponding to that, I can plot them, the error values. What will happen if you take this combination 3 minus 3? What will happen with respect to error, right? And we will plot that particular value here. Similarly, what will happen if you take wx is equal to 4 and wy is equal to, let's say, 2? So corresponding to 4 comma 2, we'll get one more point, like that, right? And this we will do for all the weights, not just wx and wy. In that particular case, we will get this kind of curve, right? This kind of net. And since they are real numbers, so there are many values which come together, and this is nothing but your error curve. So what we have done in simple words, we have considered different possibilities, different possible values of weights, and corresponding to each possibility, we have put one point on this particular curve. Now what should be our objective? Our objective should be to minimize this particular error. So that means we need to find out one particular configuration of weights where the error is minimum, right? In other words, we want to go as down as possible in this particular net, so that we can find out global minima. And once we find out global minima, we'll stop there and we will return the corresponding configuration, because that configuration will give me minimum error. This should be my objective, right? So now how to reach to this kind of location where your global minima is present? That is the question. So the idea is very simple: follow the gradient. So that means what I am doing, let me consider this particular example. I am dropping water on this particular surface. So automatically, depending upon slope of this particular surface, the droplets will follow some path. So let's say the droplets are following this particular path, and finally they are stable at one particular point. That particular point where the droplets are not moving, that will be my global minima. And I will send the corresponding weight values as my final output of training. So this should happen actually, right? So this is the objective. So now in some sense, we are trying to frame a mechanism so that we can change our weights to minimize error. So let's say you are at point P1, you want to reach to point P2, and in between you need to do a lot of changes in your weights so that your final error is minimized. Right? So how to do this? So this is the idea. So let's say if you want to, you are at this particular point, let's say P1, and the system will tell you, if you want to increase your error, then go to left. But we will do it totally opposite, because we want to reduce our error. So what we will do? We are interested in finding out minima. So we'll go right. Again, we will find out slope and we'll go right. Again, we'll find out this gradient and we'll go right. And finally, at the time we reach to the minima, at the time the surface will be flat and will stop there. So that is the idea of this gradient phenomena. For example, here, this is the valley and we are interested in finding, reaching at this particular point, right? At this particular point, the error is minimized, and if we draw the gradient, then actually it won't have any length, but just for simplicity, I am drawing it. But the surface is flat, and that is corresponding to the point where error is minimized, and we actually want to reach there, right? So how neural network will reach to this particular point? That is the next question. And to answer this particular question, we are going to learn back propagation. So basically, what we are going to do now, let's say for one configuration, we have found the error, right? And now, along with error, we have also found the gradient. So now, with the help of gradient, we are going to send messages to all the neurons whether they should increase their weights or decrease the weight. Right? So for each, it's a kind of binary thing. We'll say either to go up or to go down to all the weights which are present in our system. That's what backpropagation does. So let's see how it does it. So basically, what we are going to do, let's say this is my error. How sensitive this particular error with respect to this neuron, which is nothing but P1. That information is sent to here, and then accordingly its weights are adjusted. Similarly, weights of P2 are adjusted. But these two are not alone because again they are highly interacting with their previous layer. So this similar kind of adjustments must be done with respect to previous three neurons also which are present at this particular layer, and similarly which are present at layer 2, 4 neurons. Right? So all the weights are, the information regarding error is sent to all the neurons of the network in layer wise manner. This is nothing but back propagation where we are nothing but adjusting our weight so that ultimately we can reach to the global minima. That is the objective of this task. And the one more interesting thing here which I would like to highlight is if you see these 4 blocks, then in each block the red lines are different. So that means this is communicating with this 3. This, in other words, these 3 are communicating with this, right? Because the weight of this will be changed according to weights of this 3, like that. So it's backwards. So that means it's coming from right to left, right? So that means this is changing. At the same time, this is also changing, and this is also changing, and this is also changing. So we can do this 4 processes, process 1, process 2, process 3, process 4 in parallel, because there is no interaction among neurons which are present at the same level in this particular case, right? So we can do these processes simultaneously, and parallel processing is possible. We can use GPUs and we can get good results in terms of time also by allowing parallel processing of these processes. And finally, the information regarding error will also reach to the neurons which are present at the very first level, and accordingly the adjustments will be done. So this is fine, but now the next important question is how fast you are going to change these weights. So you are following this path, but at what speed? You are at point P1 and you want to reach to P2. So how fast you are going to follow this particular path? So that is nothing but corresponding to that particular thing. The parameter is called learning rate, and this is very much important, right? So now let's talk about learning rate. How fast these changes will be done, right? Because that will decide how fast you will reach to global minima and ultimately reach to the final output. So let's consider the case where your learning rate is very slow. For example, your learning rate is 0.125. So you can see you are here, you will go to just here, you will go to just here. So you are very slow in this particular case. What if your learning rate is too high? So let's say you are here and you are directly jumping to here and your minima is missed. So you are overshooting here, right? And then you need to come back and you may reach to here, but again, this is missed, right? So this kind of issues are there with respect to learning rate. You can't keep it too low. At the same time, you can't keep it too large also. In some cases, what will happen? You will oscillate. So this is the curve and this is corresponding error. So you can see at one point your error is near to 0, but now you are oscillating like this. You are going up, down. Because now what is happening? You are here, and now since learning rate is 0.125, you will reach to here, then again you will come back here, then again you will reach here. It's like that, and you are not reaching to 0. So that is the idea. That is the issue regarding this value of learning rate. So again, 3 different cases are considered, as you can see. learning rate 0.025, learning rate 0.05, learning rate 0.1. So generally it's kept around 0.2, right? Most of the system 0.2 to 0.3. Again, it depends upon your application, but generally the value will be like that. And here, as you can see, the corresponding error curve as well as gradient, right? So in some cases, what you can do, you are not just taking downward path, but you are also taking one parameter, which is nothing but alpha, right? So what you are going to do, you will find out gradient and you will move alpha times gradient, let's say, right? So those kind of things are also permissible, right? So you can change this parameter. There are many ways of doing it, right? So here also, like I mentioned earlier, if your learning rate is too high, then you will oscillate like this, right? So initially you're tending towards zero, but then again oscillation starts. Again, here also, as you can see, in some after some epochs, so okay, so one more keyword which is important, which is nothing but epoch. So let's say you have 2000 images and your system is taking one pass of this 2000 images. They are using them one time. Then it's called one epoch. In other words, iteration. One iteration means one epoch. You can remember like this, right? So epoch. Right? So one epoch means one iteration. Okay. So after two iteration, your error is low, but then as you can see, again suddenly error jumps and so on. Here also, as you can see, you are oscillating towards minima, right? And so on. So there are some different kind of schedules also where what you are going to do. Initially, you will keep high value of this learning rate, and then you will decrease this learning rate exponentially, right? So this is one way, right? Where what you are doing, you are exponentially decreasing your learning rate. Here, in second case, what you are doing, for some epoch, you are keeping your learning rate constant and then you are decreasing it exponentially. Here, you are doing stepwise decrease in terms of learning rate. And here you are following some different patterns. Again, stepwise decrement is there, but your steps are not uniform. Here, for the four iterations, you are keeping the same learning rate and then you are decrementing it like that. So that what is the objective of all these different schedules? Ultimately, you want to reach to global minima fast. That is the objective. Yes, any questions? If you have any questions, then you can ask. Okay, fine. So now, okay, fine. So now, again, there are some optimizers which will help us to do this particular task. So we don't need to worry, at least for the initial programs, initial task, we are not supposed to worry about this parameter. There are some optimizers which will set the learning rate for us. So mostly we are going to use Adam optimizer. And you can see the corresponding line also. So after around 600 or 700 epochs only, this particular optimizer will give loss which is close to zero. Correct? So that is the idea of this optimizer. Okay, fine. So now there is one last issue which we need to discuss, and then we can start with the hands-on. The issue is overfitting. So what is the meaning of this term overfitting? So let me consider one particular example. Okay, so let's say uh, the task is to classify different animals. Okay, and like I mentioned earlier, what we are going to do, there are two kind of where the data set is split into two. The first one is training data set, and the last one is test data set. And we are going to use only training data set, which is roughly 70 to 80% of the original data. Okay. And now let's say there are different images of cats and dogs, right? And in our data set, in the training data set, what is happening? Every time uh, if there is a picture of dog, then the dog is sitting on a sofa, right? So there is some sofa, right? And the dog is sitting on this sofa every time if picture of dog is present. Then after some iterations, what will happen? The system will focus on sofa, not on dog, right? So what it will do, it will just check whether in my image sofa is present or not. If sofa is present, then straight away it will say the image is of dog. So after few epochs, what will happen? Your training accuracy will increase, because what will happen? You are doing this cheating. You are just saying whether sofa is present or not. If sofa is present, then you will straight away give output that the image is of God. The image is of dog, right? So that means your system is focusing on less important or tiny features which are not at all important with respect to our problem statement. What was our problem statement? Our problem statement was to recognize different animals, not to recognize sofa. But now the system is focusing on sofa, right? So in training it will work, but at the time of test, you will be able to see that there is a drastic increase in error, because it may possible that in the test case there is a separate image of dog without sofa, and system will still say there is a separate image of, let's say now you have image of cat which is sitting on sofa, and now your system will say it's dog, right? So this type of error will come, and this is coming because of overfitting. So instead of focusing on actual features of your problem, your system has become over smart, and it is focusing more on tiny features which are less important with respect to your problem statement, right? So it's like this. Let's say you are designing a system which can automatically say true or false, and in your training what is happening, every time the third statement is false. So now what your system will do, if some set of statements is given, then third statement it will automatically say it's false, even without checking its content. So this is cheating, because the system is focusing on patterns which are actually not important, right? So now this won't work in the case of test, because in the case of test this pattern may not follow. This is the pattern which the system has learned from the training data. And like I mentioned, the system can use training data again and again. So its accuracy will improve with respect to training. But when when we actually give test at that time, this particular error will be revealed. So now the next question is how to solve this particular problem. So there are many regularization algorithms, but the most famous and the easiest one is dropout. So what is the idea of dropout? So let's say I have 1,000 different neurons which are present at this particular layer. I don't know which of these 1,000 neurons are over smart, or which are learning less important features or tiny features which are irrelevant to my problem domain. So what I will do, in each iteration, let's say I'm giving dropout value is equal to, let's say, 0.3. So I will randomly select 300 neurons from this 1,000 neurons, disconnect them from my network for that particular iteration or for that particular epoch, and let the weights change. So that means without this 300 neurons, I will train my network. So why I'm doing this? Because I don't want any neurons to dominate my system. I don't want this particular neuron to focus on so far and give high weights so that the final answer becomes irrelevant with respect to testing, right? So in order to avoid this, in order to, in some sense, give equal importance to all the neurons of my network, what I'm going to do, I'm going to randomly select 300 neurons for that particular iteration and disconnect them. In the next iteration, I will put them back and I will select another set of 300 neurons and disconnect them. So over the period of time, what will happen? No one will dominate this network, right? And the importance is kind of shared, and there are less chances of this kind of overfitting if we use this idea of dropout. So this is kind of this is useful for balancing things, right? In some sense. Okay, fine. Now, the one last thing which I would like to discuss is nothing but validation. So all of you know about Coursera courses, right? So in Coursera, there are two kind of tests. The one test is like quiz, which you can give again and again. If you are not satisfied with your score, then you can revisit it. You can again give that particular quiz, and your final score will be considered, right? And then there is one exam. Let's consider the traditional offline exam, which you can give exactly once. So now corresponding to this two things. So in Coursera, there are three things. There is one material, but lecture material, which contains slides as well as video tutorials and so on. Then there are some quizzes, and then there is one test, final offline test. Let's assume that offline test is there, right? So now with respect to data set, we can also have this kind of split. The first one is training, so which you can reuse again and again. Then there is a validation testing. So what is the idea of validation? It's kind of quiz. You can give it again and again, right? So this quiz you can revisit as many times as you want, but still in some sense it will try to evaluate whether you are learning properly or not, right? So that is the same idea here in the case of deep learning also. And finally, your testing data. So this test you can give exactly once, and you can't the questions which are appearing here won't be visible to you before the examination, right? So that is the idea of this third and the most important split, which is nothing but testing. Okay, fine. So with this, we have talked about all the major parameters or terminologies related to deep learning, and now we are ready to start with hands-on. Any queries up to this point? Okay, fine. So let me consider this MNIST data set. We have already seen how it looks, right? So it's a modified National Institute of Standards and Technology database. So what I'm going to do, first, I'm going to import the libraries. So like I mentioned earlier, most of the works related to deep learning is automated. All you need to do is you need to include this standard libraries. So I've included NumPy, I've included TensorFlow, I've included Keras, and I've also included this matplotlib.python. Okay. So now the very first thing which we need with respect to our problem is dataset. So what we are going to do, this dataset is by default available with this function call. So keras.datasets.mnis.load data. So this will automatically download the data, right, for us. And the split is by default like this. Your training data contains 60,000 images and your test data contains 10,000 images. And I have used four variables here: xtrain, ytrain, xtest, ytest. So what is the meaning of xtrain? Xtrain will contain images and ytrain will contain the corresponding correct label. For example, if image of 5 is given, then value of ytrain will be 5. Similarly, the same terminology will work for xtest as well as ytest also. In xtest, The image will be given. In the white is its correct label will be given, right? Like this. Okay. So this is the length of the image data sets corresponding to training and testing partition. The very first thing which we are going to do is we are going to divide the values of each pixel by 255. Why we are doing this? Because we know that since these images are kind of black and white, the minimum pixel value is 0 and maximum pixel value is 255. So we are by doing this normalization, this our deep learning system tends to give better results. So that's why we are just normalizing our data. So now if we just print our first image, then you can see there are some values between 0 and 1, and there are some values which are totally 0, right? So if value is close to 1, that means white pixel is there, and if it value is close to 0, that means or 0 value is 0, then the pixel is totally black, like that. Okay. So now as you can see, there are total 784 different values will be appearing for single image, because the image size is of 28 cross 28, right? Fine. So this is just setup. We haven't done anything new here. And if we just check the shape of the image, then you can see it's 28 cross 28. And if we just print the very first image, then it will look like this. You can see it's 5, right? The second image is 4, like that. And if we print the first 10 entries of Y-trend, then we will get first 10 labels, first 10 correct labels corresponding to our training data. So that means the first image is of 5, the second image is of 0, third image is of 4, and so on. The index value is starting from 0, right? So I have printed second image, which is actually, here you can check, the index value 2 is corresponding to 4. The label of this image is 4. So that means it's correct. Similarly, you can verify here. The very first image, index 0 is 5. And you can check the corresponding label value is 5 here also. Okay. So like I mentioned earlier, in this particular case, so this is my data set, like I mentioned earlier, and these are the images, and corresponding to each image, in this particular case, we are talking about X train, Y train. So in X train, this image will be there. In Y train, the number 2 will be there, like that. Right? So for example, we want to do processing for this particular image 2. Then 2 will look like this. Wherever 2 is present, the pixels are having higher values which are close to 255, and for the black portion, the values are close to 0 or 0. And like I mentioned earlier, flattening is important because we can't provide this two-dimensional array directly to this neural network, right? So what we are going to do, like I mentioned earlier, we are going to convert this 28 cross 28 matrix into one-dimensional matrix of size 784 cross 1. So that is what we are going to do first. So here, as you can see, for this particular purpose, we are going to just call this reshape function. And the reshape function we will call on all the 60,000 images of training and 10,000 images of testing. So after this, what will happen? Now images will be of form 784 cross 1. Right? So we have converted them into one dimension. So this, so far we haven't done anything. This is just flattening thing. The main portion of our model setup starts here. And like I mentioned, after learning about terminologies, writing down this is not that much difficult. Still, I will share some tricks with you how to remember and how to write this model parameters. So the very first thing with respect to this model setup is this keyword dense. What is the meaning of this dense keyword? We are saying that whatever neurons which we are going to include here, those neurons are those layers are kind of dense. So that means the connections will be with all the neurons of the previous layers also. And I am going to start with the simplest possible neural network where what I'm going to do, I'm going to have 784, right? 784 neurons which will take inputs from which are corresponding to 784 pixels, and then I will have 10 neurons in my output layer. Why 10 neurons are required? Because each neuron will corresponding to one digit up to 9, so 0 to 9. And now I am saying that the network is dense, so that means each neuron of this layer, output layer, will be connected with all the neurons of my first layer, which is, that means each neuron of the output layer will have 784 different connections. That is the 784 connections to the previous layer. So that is the idea of that dense keyword, right? So the connections will be like this. This is connected to this, so on. Okay. So therefore, the dense keyword is there. Okay. Later on, I am saying, so here order is important. Like I mentioned, whatever comes last, we are going to write it down first. So output will come in the last. So we'll write down first. How many output layers, output neurons are required? 10. What is the size of input? Size of input is 784. And what is the activation function? So here we are using sigmoid. So there are two more options which we had discussed, ReLU and 10H. So here I am using sigmoid. So this is just setup. We have just told how many neurons are required and which kind of connections between them and what is the activation function. That's it. But now with respect to errors, we are not saying which kind of error we are focusing on which metric we are going to evaluate our model. For that particular purpose, we are going to give this command, which is nothing but model.compile. And here we must specify three things: name of the optimizer, which kind of loss we are considering, and what metric we are going to evaluate our system. So there are many kinds of losses, but for this particular problem, I have considered this pass categorical cross entropy loss. So you can check here the definition of this loss, how it works, right? So I will also share this this particular notebook with you, so that you can experiment. So there are other errors, other kind of losses also, right? Mean square error and so on, right? So you can check them also. And now this is kind of with these two lines, we have done the entire setup, right? So it's like we have written the code, but now we need to provide the data. Without input, the model won't work. So now we need to provide the input. And which input we must provide? Training data, right? Because testing data, like I mentioned earlier, testing data we are going to consider only once in our entire execution, right? So with these two lines, the entire model is built, right? Where the main thing is number of neurons, activation function, loss function, optimizer, and metrics, right? These parameters are important. And now we will call model.fit, and then we will provide the data. So data is stored in this particular array, x underscore train underscore flatten, and the corresponding correct labels are in y underscore train. And now here we need to specify how many iterations are required. So here I am saying 15 iterations, 15 epochs are fine. And you can see each iteration, you will find that loss and corresponding accuracy is calculated. And after each iteration, the loss is decremented. You can see initially it was 0.46, now it's 0.30. The accuracy is increased from 87 to 91 after 2 epoch. And finally, after 15 epoch, your loss is 0.20 and your accuracy is 0.93. But this accuracy is training accuracy. That means we are talking about its performance for which the model is already trained. But we are more interested in testing accuracy. So in order to do that, we are going to call model.evaluate, and now we will pass test data instead of training data. So we'll pass two parameters, because without y test, how we will be able to find out accuracy? Because in y test, correct answer is stored, and in X test flatten, the data is there which is to be provided for to the model for the prediction, right? So predictions will be done based on this data, which is nothing but X underscore test flatten. But now we want some mechanism using which we can compare our prediction with the existing answers. So existing answers are there in Y test, so therefore we are passing it also. The same thing is true with respect to model.fit also. There also we had provided the correct answers, and now we are getting accuracy of 92.6%, which is fine. But this is with respect to simplest possible neural network where there is no in between layers. There are two layers only, as you can see. The first layer will contain your input neurons, right? The neurons which are going to take 784 different pixels, and your last output layer contains 10 different neurons. So basically this is mandatory to take input. This is mandatory to give output. So we are not taking anything in between, right? So this is the very, one can say, the simplest possible model for of deep learning, and still we are getting 93% of the accuracy. So that means 93% of the times, if we give this kind of images, then the 93% of the time the prediction is correct by the system. Okay, so now our objective is to improve this accuracy. So how to do so? So now let's try to include in between layer which contains some number of neurons. Okay, so this I will explain in a minute, but before that let me explain the modification. So now what I am doing now, if you focus here, then last two lines are similar. If you consider this two, then I haven't done anything here, right? For compilation purpose, I am using the same optimizer, same loss function, same metric. I am also providing the same data, X train, Y train, same number of epochs. The only change which I have done is I have included one hidden layer here, which contains 115 number of neurons. So now what will happen now? Now we have in between 115 number of extra neurons which are connected with all the neurons, all the 784 neurons of our input data, right? And in between I have used ReLU function. Towards the end I have used sigmoid function. And again 10 neurons are required at output layer by default because 10 different classes are there with respect to values, object values, right? Or classes, right? So now with this change, if we check the final accuracy, then you can check the accuracy of training is 99.72% and accuracy of testing is 97.79%. So there is a drastic increase of 4% accuracy if we just include one layer of neurons with 115 number of neurons, right? So this is about how impact of adding just one layer, one hidden layer of neurons. But with this inclusion, if you notice carefully, then this variant model 2 will take more amount of time. You can check 2 milliseconds is required for each step as compared to if we consider this version where only 1 millisecond is required for each step, right? Why this is why model 2 takes more amount of time? Can anyone guess the answer? So the idea is there are more weight parameters in your model 2 as compared to model 1, because now this is also your dense layer, and each of this roughly 700 into 100, this many weight parameters will be increased in this particular case. This is nothing but 70,000, right? 70,000 weights are increased now. So in order to update them, more time is required, right? So therefore I've already done this and before this talk, and I'm explaining it to you like this. Okay, fine. Now this is fine, and along with this we can also analyze our output. So this is with respect to one can say by default what system is giving us, we can also manually check. For example, let's say all the predictions are stored in y. So y will look like this. It's a sigmoid function, so that there is no softmax. So we can't say these are probabilities, because if we add them, then we won't get 1. So how to, for example, if I write down y0, so that means these are the results of 10 neurons. These are the outputs which we are getting corresponding to 10 neurons which are present at the output layer. Then which one y0 is corresponding to which value, that I am interested in finding out. So for that particular purpose, I can use argmax function which is inbuilt in NumPy. So I will call argmax of y0 and it will give me 7. So that means it's saying that 7th neuron has the highest value. We can say 7th neuron is fired for this particular image. And if we actually check that particular image, then that particular image is of 7. So that means our prediction is correct with respect to this first image. Same thing we can repeat for other images also. So as you can see, we can check what is happening with respect to image 1. We are getting 2 and the image is actually of 2. And we can now print down the first 10 predicted values, and we can also print down the actual values which are present in y, and then we can compare and get the intuition how well our system is doing. We can also print this confusion matrix where diagonal entries are corresponding to correct answers and other entries are mismatches. For example, if your image is of 0, then system is telling you 6 times it's an image of 5. So that means those kind of error values are corresponding to non-diagonal values. Right? And same thing we can do with respect to model 2 also. Right? We can also print this confusion matrix, but that number of zeros will number of non-zero values will be less, because the model 2 is slightly more accurate with respect to model 1. Right? So now this is with respect to MNIST dataset. Now we will consider one more dataset, which is nothing but Cypher10. So now what is the difference between MNIST and Cypher10? So MNIST was black and white, but the Cypher10 is color. And again, there is a change in image size also. You can see the image size is 32 cross 32 in the case of Cypher10, whereas in the case of MNIST it was 28 cross 28. Right? So that is the change. And here also there are 10 classes. You can see airport images, airplane images, automobile image, bird image, cat image, deer image, dog, frog, and so on. And there are 50,000 images which are corresponding to training, and 10,000 images are for test images. Right? And again, this we are doing nothing but supervised learning. So for each image, we already know what is the underlying correct class or correct name for that particular image. Okay. So with respect to this MNIST, I just wanted to highlight one more thing. There is an inbuilt function in Keras for flattening your input also. So we'll see it in the next model, how to flatten your data directly, right, at the time of model setup. That thing is remaining. Okay, fine. So now with respect to Cypher10, again, what we will do first, we will load the data. So again, we'll get this 4 parameters: X train corresponding to image, Y train it's corresponding correct answer, X test again image, Y test its corresponding correct answer. 50,000 images are in training, and 10,000 images are in testing. And since there are 3 channels corresponding to R, G, and B, if you print it down, for example, if you print down the first image, then it will look like this: 32 cross 32 cross 32. Right? So it's a 3-dimensional array, and then the corresponding labels are also listed like this: 6, 9, 9, 4, 1. So what we want to do, we want to reshape, because this is not the correct template for knowing about answers. So what we are going to do, we want this kind of answer: 6, 9, 9, 4, 1, not in arrays. So therefore we are going to call this particular reshape function, so that we can get this kind of output, so that we can compare our output properly. Right? So this is a small change which is done in with respect to Y-train. Now these are the classes, and now this particular function plot sample is written so that what you can do, you can call this particular function and print an image along with its correct label, right? So that is, for example, if you call this particular function with x10 y10 0, then basically zeroth image from the training data will be printed along with its correct label. That is the idea of this function, right? Just for verification purpose we need this kind of thing, right? Similarly, for example, if you call second image then truck, and this data set seems difficult. You can see the images are very tiny and it's very much difficult even for human eyes to identify whether this particular image is of truck or some other vehicle, right? The very first thing is similar. First, we are going to divide our data set by each entry of our matrix by 255 so that we can, again, relative values will survive, but all the values are between 0 to 1 now, like this. And the most important part starts now. So like I mentioned earlier, there is an inbuilt function in Keras, which is nothing but layers.flatten. This function will automatically convert each image of size 32 cross 32 cross 3 into single dimension matrix, right? So that is the task of this layers.flatten function. So automatically your array will be converted into one dimensional array. That is the task of this flatten function. Then we have one hidden layer of size 3000 neurons, one more hidden layer of size 1000 neurons. The underlying activation functions are value. And finally, we have 10 classes. Why it is 10? This 10 is mandatory because we want to classify our object into one of these 10 classes. So therefore, we are going to write down this 10 pixels which are corresponding to output layer, and the final activation function is nothing but sigmoid. And again, I am using the same setup. Loss is sparse categorical cross entropy, matrix is accuracy, optimizer is Adam, which we already know, and this is compilation. So the entire setup is done up to this point. So we have used roughly 4010 plus this number will be 2700 plus. So roughly 7500 number of neurons we have used in this particular network, right? And now we are saying we are training it just for 5 epoch. Okay, so number of epochs are 5, and we are passing our training data here. This is my images x10, and y-train is nothing but its corresponding correct answer. And you can see the accuracy is very low. Even the training accuracy is very low. Forget about testing. Training accuracy is 46%. So that means roughly 46% of the times you are going to give a correct answer, which is very low. Fine. So now, so far, we have seen a simple version of artificial neural network, and we have seen that for some cases like black and white images, it's working nice. By adding hidden layer, we were able to produce good results in terms of accuracy. You can see 97% accuracy we have got. But something is missing here where we have seen that the accuracy is only 46%. And the problem is difficult, but still we expect our automated system to work better for this kind of problems also. So now we need to think about its solution. So that is the this is the motivation for learning about the next topic. Okay. So now let's think about which problems will occur if we follow the same methodology for colorful images also. For example, let me consider this image of koala. So let's say we only know how to solve artificial neural networks for like this for images. Then what is the problem? Let's say I consider this image of koala. Then the image size itself is like this, 1920 cross 1080 cross 3. So this is roughly 6 million. So that means mandatorily you need to put 6 million neurons at your first layer just to take input. Forget about the processing, right? So for processing, let's say I am keeping one hidden layer of size 4 million, right? So now this hidden layer, this name of this layer is hidden. So that means every neuron of this particular neuron is connected with all other neurons of the previous layer. So that means 6 into 4. We need to take care of 24 million different weights at the time of back propagation and gradient descent, so on. Right? So that means in no way we can process this in real if we continue with the existing approach. The most problematic thing is number of neurons, because this data is too much. How to and this is just for one image, and we are talking about thousands and millions of images. How will you how even with supercomputers you won't be able to perform this kind of computation. So this is the first disadvantage of using our existing artificial neural network technique for image classification. Apart from this, there are other disadvantages also. So let's discuss about them. Just a second. Okay. So one more disadvantage is this particular system is not location invariant. So that means if for example, if you remember, then in the case of MNIST, all the images were located in the center. But if I give image like this, where number is not located in the center, then the system may not give us good accuracy. So that means the system is very much dependent upon arrangements of data. If location is shift, then even for the same data item, your system may give you inaccurate results. So it may possible that system is able to predict 9 correctly if 9 is coming like this in the center. But if you provide 9 here, then it may possible that your system gives you the wrong result. Why? Because every time system is used to give more importance to pixels, and that means neurons which are corresponding to the pixels which are present in the center of the image. But now you are doing something else. You are putting your main content in the left side of your image. So will this change won't be handled properly by your artificial neural network. So that is one more issue, right? So like I mentioned earlier, the first issue is too much computation. For example, in this particular case, we know 24 million weight parameters are required, which is a very big number and difficult to compute, right, on the machine. Even store, forget about compute. Second thing is, like we have just discussed, sensitive to location of object in an image. If image is appearing in the center, then it's fine. But if image is coming towards left, is appearing in the left corner, or let's say right corner, or some with some rotation, then your ANN won't be able to detect it properly. So in some sense, what we want some location invariant feature. We want some mechanism which is not dependent upon location. Second thing which we need is we need space efficient solution, because space as well as time, because 20 in order to solve in order to save 24 million parameters, too much space is required, and also computation power is also required to update these weights, right? So we want space efficient as well as location invariant solution. Apart from this, we are also interested in killing overfitting. Now ANN tends to overfit our data. Why? Because it treats local pixels same as pixels far apart. If I give it collection of images like I mentioned in earlier example where dog is sitting on sofa, then the system doesn't know which object is important, dog or sofa, right? And it may possible that the focus is shifted on sofa, not on dog, right? So we also want to system which doesn't support overfitting, right? So all these problems are solved by convolution neural network, and now we are going to talk about it. So the very first thing is, what is convolution? What is convolution operator, right? These things we must discuss, and before that we will talk about filter. So what is filter? So let's say I want to identify whether this circular pattern is present in my image or not. So for that particular purpose, what I will do, I will form one matrix and I will put 1 if some portion of my pixel is black, and I will put -1 if the pixel is entirely uh, white, we can say, right? So for circular pattern, the matrix will look like this, because in the case of circular pattern, what will happen? Sorry, all this will be plus, and inside we are going to put -1 to differentiate, right? So it's like this. You can see this square. So all the entries in the squares are 1. In between, there is white space which follows a particular pattern. So we'll put -1 there. So this is nothing but your circular pattern. Now, what is the advantage of using this circular by representing this circular pattern via this kind of matrix? That is the question. So now, if I do dot product of my 3 cross 3 submatrix of my image with this particular matrix, and my answer is, let's say, 9, then I can say that that particular pattern is present in my image. For example, if you just multiply this matrix with itself, then it will become clear. So it's not a traditional matrix multiplication. The idea is dot product. So this one will be multiplied with this one. This one will be multiplied by this one. This one will be multiplied by this one. This -1 will be multiplied with this -1, and so on. And finally, the summation is 9. And if we normalize it, then we will get 1. So whenever 1 appears, so that means the corresponding pattern. For example, 1 is appearing here. So that means after 1 shift, the pattern is present in my system. So we can verify this. You can check this matrix, and this particular matrix has this particular pattern. So this pattern is identified by this particular filter. Whenever 1 appears in this particular feature map, I can say the pattern is present in my original image. Now the question is how to formulate this feature map, right? How to construct this feature map. So it's very easy. What we are going to do, we are going to start with this particular matrix in left to right manner and top to bottom. So first we will consider this matrix, and we are going to multiply this matrix with this particular filter. So what is the task of filter? The task of filter is to identify a particular feature which is present in my image. So currently I am considering loopy feature, whether loop is present in my image or not. So first I will multiply this matrix with this matrix, and I will get -1.1. Then I will shift by 1 location, and now I will focus on this matrix, and then I will multiply this second matrix with my filter, and I will get 1. And then I will again increase size by 1. So now I will consider this matrix, and then I will get this third entry. And then I will repeat the same process with respect to second row, third row, and so on. So like this, I will get feature map. So what is the idea of this particular feature map? It will identify all the loopy pattern which is present in my image. Right? Now, with respect to 9, this loopy pattern is identified. After loopy pattern, we want vertical line. You can see 3 ones are appearing in straight line. So that is my second filter, and my third filter is diagonal line. You can check these 3 ones are appearing in the diagonal. So basically, I will repeat the same process with respect to these 2 filters also. So now you can check. This is with respect to 9, and the same circular pattern is also identified with respect to 6 also, because in 6 also we are getting the same. Okay, just a second. Okay, sorry, let's continue. I hope I'm audible. Can anyone confirm?
Yes, sir.
Yes, sir, you are audible.
Okay. So now instead of 9, let's consider 6. So in 6 also the same kind of circular pattern is present, but now location is different. Now it will coming here in the bottom. And if we talk about other patterns, then what is my primary interest? I will consider one more filter for finding out this vertical line, and one more filter for finding out this diagonal line. And basically, I will generate 3 different kind of feature maps. And if I club them, then I will be able to identify whether the entire 9 is present in my image or not. So that is the idea. So by doing so like this, so we have stacked these filters one above another. So basically 3 filters are there, and if we get 3 ones which are aligned in my feature maps, in 3 different feature maps, then I can finally say whether this particular image contains 9 or not. And the important thing, there are several important things with respect to this idea of filter. The very first thing which we must notice is this is location invariant. What is the meaning of this location invariant thing? Irrespective of 9 is present here or here or here, my system will be able to detect it ultimately, because now I am traversing the entire image filter by filter. Like first I will cover this portion, then I will cover this portion, then I will cover this portion, then I will cover this portion. So I'm not focusing on only specific region of my image. That is the very first thing with respect to filter. The second thing is the same idea which image is trying to capture is conveyed with the help of feature map. And now you can check the size of image and as well as feature map. The image size in this particular case is let's assume 28 cross 28, but the feature map size will be definitely very less as compared to this original size, because now we are just giving answers with respect to a particular filter whether a particular feature is present in my image or not, right? So the dimension is also reduced, and this reduction in dimension will ultimately help me in terms of less number of neurons and hence less computation with respect to overall modeling, right? So that is the key aspect with respect to filter. Now, what is the idea of this minus 0.11? Minus 0.11, if 0 comes, then it makes sense that the pattern is not present. Minus 0.11 doesn't make any sense, and in future this people will trouble us because they will take a lot of power in terms of in terms of computation. So what we are going to do, we are going to apply one value function so that this remaining entries becomes 0, because they are anyway not making any sense. If number is some slightly greater than 0, then maybe we can say pattern is slightly present or something like that. But if number is 0, that means straight away the pattern is missing in my image, right? So that is the idea. So therefore we are also providing this value function. Now after doing this processing with respect to filters, there is one more aspect of convolution which is called pooling. And I'm talking about max pooling here. There are other types of pooling also, which is corresponding to average pooling or mean pooling. So what is the idea of this? So let's say this is your feature map. And in feature map also, you are interested in dominating terms only. So let's say I'm considering 2 cross 2 sections, and I'm identifying the maximum value in each 2 cross 2 section and I will put it down. So this is again helped me drastically with respect to dimension reduction. So now initially I had started with images. Now instead of images, my focus is on feature maps, and in feature maps I have reduced computation by applying ReLU activation function so that the negative values have become 0. And now again in feature maps I have applied pooling so that the dimension is reduced drastically towards the end. So all this we are doing just to resolve those three major issues with respect to artificial neural network, right? So now, as you can see, even if your location is shifted, you will be able to identify the pattern like this. So you can see the circular pattern is present here. You will apply value, and after max pooling 1. So now I want to just highlight this thing. So you can compute 1, 2, 3, 4, 5, 6, 7. So this is kind of 7 cross 7 image, and if you can see the essence of the image, which is nothing but the circular pattern. Presence of circular pattern is still noticed here after applying max pooling on the same image, and check the size of this particular image. It's 4 cross 2. So with 8 entries you are conveying something, and here you are conveying this kind of same thing with 49 different entries. So this is the advantage of applying convolution. This is with respect to one feature or one filter, but in practice we require more filters. So for example, with respect to koala animal, we can have 3 filters corresponding to eye, nose, ears, as well as body and tail. So let's say 5 filters are present initially, and after that we can again have one more layer of this convolution plus pooling, where the focus will be on higher order features. For example, eye, nose and ears will constitute one more feature which is corresponding to head of the koala animal, and legs as well as tail will focus on the body of your koala animal, right? So, and this remaining aspect we already know. This is our artificial neural network. After flattening, we are going to provide this feature maps. After pooling, we are going to provide it to the artificial neural networks. But now our problems, our life has become easier. All the issues are resolved now. The size is reduced drastically, so less number of neurons are required. Less number of neurons, hence less number of weight parameters, less computation time. Location invariant feature, because now we are scanning this entire image, so we won't be able to miss eyes of this particular animal, because we are going to cover this entire image line by line from left to right, top to bottom. So there is no chance of missing any important feature, right? So this is the core idea of convolution. So what we are going to do, with respect to convolution, we are saying that we are reducing overfitting. We are providing location invariant feature. With respect to value, we are speeding up the training because we are ignoring the negative numbers. With respect to pooling, again we are reducing dimension as well as computation, and it will also help us in reducing overfitting because unnecessary features will be eliminated by applying aggregation functions, and this will help us to make our model more stable towards variations. So now this seems very interesting and fascinating, but one can ask, till it looks like rule-based system or expert systems, because who will decide which features are important for the given image? And again, we need to give so many filters. For 9, we have identified 3 features. What will happen if I give you a set of images with respect to X-rays? Then how will you identify which features are important for those images? So here, deep learning libraries helps us. We don't even need to specify these filters. All we need to do is we need to specify number of filters. How many filters are required? This we need to specify. And what will be the size of each filter? For example, I can say I need 64 filters, each of size 3 cross 3. I don't know which feature this particular 64 different filters will focus on, right? We don't know which features will be captured by this 64 filters, but still we will get good results, right? And that's what matters. So the idea is, here no one will ask why you have chosen 64 filters or 128 filters, why you have considered 3 different layers of convolutions, why not just 2. As long as you are getting good results and you can prove it experimentally, then with the help of experiments, if you can show that you are improving upon the existing results, you are done, right? So now let me demonstrate the power of convolution neural network by considering the same problem. But now what we are going to do, we are going to apply convolution. So as you can see, this much is the different. The remaining thing you already know, right? You know what is the meaning of flatten. And here one more interesting thing. Here even I don't need to specify how many neurons are required at the very first layer. Why? Because I don't know. I don't know what will be the dimension of my matrix or image after performing this convolution as well as pooling. The system will automatically detect how many how many neurons are required at the beginning. Then we have used one dense layer of size 64, and finally 10 neurons are required at the final layer because we have 10 different object classes. Because again, I'm talking about the same problem, which is nothing but cipher 10, right? So here we know that 10 different classes are there, namely airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck, right? So now this we already know, so we are not going to revisit this. Very straightforward. We are So this is my first layer of convolution. So what I am saying, I need 128 filters. Each filter is of size 4 cross 4. My activation function is value, and my image is of size 32 cross 32 cross 3. And this is again setup. I am not providing any data. This is just setup. And after applying this filter plus value, I will use max pooling operation. Right? So 4 entries will be replaced by 1. That is the idea of this max pooling. Then again, we are done with one layer of convolution. We'll repeat the same process. I have become mindless now, and I'm just using the same trick again. Same number of filters, same size, same activation function, same input shape, and max pooling operation with 2 cross 2 size. So this is nothing but the setup of CNN. The only thing which is new is this, where you need to specify number of filters, size of filter, right? Size of filter is denoted by kernel size, which is 4 cross 4 in this particular case. Activation function, which is value by default, and pooling operation. So here we are using max pooling. You can also use mean or average pooling, right? It depends upon your problem. Okay. And after this, what we are going to do, again, we will first compile this with Adam optimizer. Same loss function I am using. The metric is accuracy, and now I am providing training data. So training data, in order to provide the data, we will call this particular fit function, and number of epochs 10. You can see after one iteration itself, you can check the accuracy is 43%. And after 2 iterations, we are surpassing our previous best. Our previous best was 46%, if you remember. And now we are getting 57% of training accuracy. And towards the end, after 10 epochs, you can see accuracy is 74%, which is good for this particular problem, because as I mentioned earlier, the images are very tiny, and for some images, even with human eyes, we won't be able to give correct answers. And we are improving drastically with the help of CNN. And with respect to test data, the accuracy is 68.37%. Right? And now we can check how well we are doing by like I mentioned earlier. What we need to do, we'll print down our first 10, let's say, predicted values and first 10 actual values, and then we can compare and get insights how many times we have got correct answers and how many times we have got the wrong answer. For example, this is my correct answer, right? Sorry. This is my predicted answer, and this is my correct answer. And you can compare 33888800. But now this is my first mismatch. The predicted value is 4, but the actual value is 6. One more mistake. The predicted value is 3, but the actual value is 6. Remaining 4 entries are correct. 1631, 1631. Right? Like that. And then we can actually print those images and see for which kind of images our system is not performing well, and so on. So this we have done with respect to colorful images like this Cypher 10. Now I have one question. Can we do the same thing? Can we apply CNN on normal black and white images also with respect to MNIST dataset? This is the question. We have already applied uh, traditional artificial neural network with respect to MNIST dataset, and we have got accuracy of 97.79%. Do you think there is a possibility of improvement if we apply CNN here, or we can't apply? We can apply CNN only on colorful images. What is your view?
So, am I audible, sir?
Yes, you are audible.
Yeah. So, I think that we should be able to apply CNN to the image. But the thing is, like, while we initialize it, we have given like, but then three-dimensional matrix. So that we can change it to like a two-dimensional matrix in the case of an black and white. And if it is a grayscale, then maybe we can have it as a three-dimensional. So I think it's possible to apply
Yes, yes.
CNN over
Yes,
black
so
and white.
let's check this. So here what I have done, I have applied the CNN on our MNIST dataset. And as you can see here, the only change is, the major change is here. I've used 48 filters initially, each of size 3 cross 3, and the input shape is 28 cross 28 cross 1. Why 1? Because I have just one channel. This is black and white image, right? So there is only one channel, and the activation is value, kernel size is 3 cross 3. Again, max pooling 2 cross 2, and I've reduced the filters in the second layer. So generally, what will happen? First level filters will occur in the first layer, at the first layer, and later on we focus on the higher level filters, so higher level patterns. So generally, we put these values which appears afterwards less than the previous values, right? So for example, if I introduce one more layer, then filter size should be 60, right? Like that. And again, it depends upon your data set also, and you can experiment, but that is the idea. And what I have done, I have used 64 neurons in addition to this. We don't know how many neurons will come here, but can you tell me some estimate in terms of less than or greater than? Initially, for the straightforward solution, if you remember, then in the straightforward solution, how many neurons were required at the very first level with respect to MNIST dataset? Can anyone answer? We had already done it here. Hmm. How many neurons are required at the very first level in this particular model?
For an input, we took 784 neurons after
Yes.
flattening.
Yes, 784, because the image size is 28 cross 28, and 28 cross 28 is nothing but 784, and each neuron will take one pixel value. That was the idea. But now, in the case of CNN, what will happen? This particular number, if we reach to this particular highlighted line, layers.flatten, the number will be definitely very less than 784, because now we are processing our input in terms of filters as well as pooling operations. So the dimension will be reduced drastically. And apart from that, we are using 64 neurons in the next layer and 10 neurons. This 10 neurons are again required because we want to classify our image into one of the 10 categories from 0 to 9. So that is the idea of this CNN network, this modified network. And now if we compile this modified CNN network with the same set of optimizer, loss, and matrix function, Then just after 5 epochs, you can see the accuracy is 99.49, which is higher than this one. If you can see, then here we were getting accuracy of 99.72, but this includes one hidden layer of size 115. If we just consider this one, then we are improving significantly. And again, it depends upon number of epochs also. If we increase number of epochs, then it's likely that we improve upon this also. And with respect to testing data, right, our accuracy is improved to 98.98%. Whereas in the case of this, even if with hidden layer, I guess our accuracy was around 97%. We can verify here. It will come. Yes, it was 97.79%. This is with hidden layer. And with CNN, we are able to improve upon it. And now this is better because 98.98 is roughly 99% of the time we are doing, we are able to predict correctly. Okay, so this discussion was necessary to understand the next topic, which we are going to consider for the next talk, which is nothing but graph convolution neural network. So we'll continue from here in the next talk on Thursday. Thank you. Any queries?
So if you have any queries, you can ask now. So sir, we have one query.
Yes.
This is how deep learning can be used in social networks.
Oh, so for that particular purpose, please attend the next talk. So we are going to talk about it only now. But this was necessary because if I directly start with a graph convolution neural network or graph attention network, then again, you won't be able to understand about this parameter settings and all those things. So similar kind of things we are going to do with respect to graph neural networks also, but for that some kind of setup is required because the basic question now one can ask is how we can apply CNN on graphs. So the straight away answer is no, we can't apply it directly because as you can see, images are very regular and not all graphs are regular, we can say, right? Because if we consider any social network, then not all the social networks are regular. So we can't apply this particular concept directly. Some modifications are required and different kind of loss functions are required. So those things we will study and in detail in the next talk.
Sir, Vani here. So my question
We can take questions in the next session. So I think we should wind up with this session. So let us take other questions in the WhatsApp group or maybe in the next session if possible, because it is already delayed by 30 minutes and maybe we have to wind it up soon this thing. And so yeah, we can definitely take up the other questions in the next round. And yes, you can also share your thoughts because I have seen in the group actually most of the questions are related to CNN and other neural networks. So let's wind up with the session, and I think I believe that we should take up more questions in the next session. So yeah, so I think
I hope you were able to understand, I guess, basics of deep learning. I'm not sure, so that's why I just wanted to know.
Right, sir. Because actually it is good idea to pick up from network science to deep learning with the basics. So it was very much required and it is very useful session indeed. Yeah.
Okay, thank you.